there are there are variations in the way the equations are written, it would be a good idea for you to stick to only one and to one and only one equation, so that you avoid getting confused in relation to which formula is supposed to have a negative, which one shouldn't have a negative. So just stick to one. Just copy the formula on, you write it on a piece of paper, stick it somewhere, you keep looking at it for 2, 3, 4 days, it sticks and you forget about it. So after plugging in all the values that we have into that equation,
Many
we see
people
that
believe,
the answer that
many
we are
people
getting
believe
is
confidence
that one. So
only
this is
comes
something
when
that you
you
probably
look
might
good
just
in
need
the
to go
mirror
through
or when
in your free
people are
time
watching
on
you.
your own.
But we believe
Okay,
confidence
so
comes from within,
with that said,
from
then
the energy,
we
freedom,
can
and joy
now
you feel
start
when you
from
express
where we needed
yourself.
to
That's why we're
start
bringing
from,
this experience
which
outdoors,
is our next
creating a
slide
space
here.
where dancers and creatives
Okay,
many
where we talk
people
about the boiling point and normal boiling point of substances. So boiling point is defined as the temperature at which the equilibrium vapor pressure of a liquid is equal to the external pressure. We apologize, my friend. We would have loved to have gone through everything step by step to make you understand, but we sorry, we have to move forwards. I just hope that that
And
helped somehow. It's okay?
sure, sure. Yes, sir. Thank you so much.
Sure. Okay. So the the normal boiling point is the temperature at which a liquid boils when the external pressure is equal to 1. So in other words, we take note that the normal boiling point fixes the external pressure at 1 atmosphere. So from the table,
many people
the
believe
higher the molar heat of vaporization, the higher the boiling point. That's what we should take note of. You see that water on this particular table has got a molar heat of vaporization of 40.79 kilojoules per
many
mole,
people
and
believe
its boiling point is equal to 100 degrees Celsius. When you compare with argon, argon with a very small molar heat of vaporization of 6.3, it has got a boiling point that is negative 186 degrees Celsius, which is way smaller compared to the other one there. Then another concept that we might want to make ourselves familiar with is what we refer to as the critical temperature and the critical pressure. So the critical temperature is the temperature above which, when it goes beyond that, is the gas cannot be made to liquefy. So no matter how great the pressure is that we would have applied, it is not going to liquefy. Then the critical pressure is the minimum pressure that must be applied to bring about liquefaction at the critical temperature. So if we're going to need to cause a gaseous substance to liquefy, then we need to apply the minimum required pressure for that particular purpose. So to I understand I might be a little bit too fast, so I apologize. I'm trying to beat on time. I'll slow down a bit, however. Okay, so to make us understand everything that I've just talked about here, let me give you an example of a specific substance that behaves in a certain way, which makes it possible for us to understand that when we cross the critical point, the substance may change its phases. And this particular substance is sulfur hexafluoride. So sulfur hexafluoride has a critical point at which the temperature is 45.6 degrees Celsius. The pressure is 37.6 atmospheres. Okay, those two conditions. So the temperature is attainable. You can manage to achieve this temperature in the lab. The pressure also is attainable. Unlike if you decided to settle for water, water has a critical point of 374 degrees Celsius. So for you to, and if you're able to remember from the previous table, we had, was it 219? 219.4 atmospheres as the critical pressure. So for you to achieve this temperature and that pressure in the lab, it's quite a daunting task. It's quite it will be a challenge of sorts. But this temperature is easier for you to achieve, and that's why mostly we use this particular substance to demonstrate the concept of critical uh, temperature and pressure. So I'm going to try and um, explain what is in each of these test tubes, that what is happening in each of these test tubes. But we'll do well to recall that we had said that uh, the critical point is the point at which the temperature and the pressure will have to be above, or these are the temperature and the pressure that will have to be attained for the substance to be in a specific state, above which you're going to notice that the liquid and the gas phases will become indistinguishable. You'll not be able to see that your substance is in a liquid state or in a gaseous state. So let me try and quickly explain what is happening in each of these test tubes. So in the first test tube, let me remove this. So in the first test tube here, the temperature is below the critical temperature. So we get to see, a sharp meniscus, okay, a sharp meniscus, and the the liquid part of this substance is at the bottom. The gaseous part is on top. And since the densities are very different, we have a clear interface between the two of them. And you would refer to this as being the normal behavior for sulfur hexafluoride, such that if you were to heat the substance a little bit further, you will notice that the liquid level is going to drop as more evaporation takes place, and the particles will change into a gaseous substance. So when the temperature is above the critical temperature, in which case you would have gone beyond this temperature here, okay, the meniscus disappears. The substance is still in there, but it disappears. So the liquid and the gas phases, the liquid and the gas densities will converge. They converge until they are identical. So you get one homogeneous supercritical fluid that is going to fill up the whole tube. So this supercritical substance is a substance that would have reached a state at which you're not able to see the gas phase. So there will be no more phase boundary that is going to exist. The gas phase and the liquid phase would have converged, and they form a supercritical fluid. Okay, so what is the distinction between the liquid and the gas phases will simply just vanish. They will disappear. But when you have a temperature that is equal to the critical temperature, such as what we see in this particular third tube here, sulfur hexafluoride is right at the critical temperature, in other words. So we notice we get to see this milky appearance, and this is a normal behavior. I mean, this is the behavior of sulfur hexafluoride when it would have reached its critical temperature. So the what is the you will see, this is, in other words, this is the signature that you are at the critical point for this substance the moment you start to see this appearing. Okay, it's a little bit milky, but then you can still change the conditions slightly, where, as we notice in the fourth tube here, what you do is you're going to cool the substance further to the point that it deposits as a solid instead of condensing as the liquid as we saw here. So it deposits as a solid. So when that happens, we see that at the critical temperature, only the liquid gas boundary is going to be eliminated. the solid gas and the solid liquid boundaries still exist. So the critical temperature does not entail that there's going to be an end of all phases. It is just the liquid gas phase or line on the phase diagram that is going to disappear. All the other lines, like we are going to see, I'll show you some phase diagrams later on, will still be present in the phase diagram. So the solid phase, here we have changes from we were interested in the what is the melting point, the melting point of a solid, or the freezing point of a liquid substance, which is a temperature at which the solid and the liquid phases are going to coexist. So when the two points, when the two phases will coexist, that is what we are really interested in, and our focus essentially here is just on the melting point and the freezing point. Well, of course, we've got all the phases showing here, but only on these 2 points. The molar heat of fusion. For the molar heat of fusion, you are looking at the amount of energy that is required to melt one mole of a solid substance at its freezing point. So essentially what you're doing here is that you're applying heat energy to break the some of the bonds in the crystalline lattice, but not all the intermolecular forces. So the particles do not really get to disintegrate like they are going to be to exist as individual particles, but what you will have only done is disrupted the crystalline lattice itself by applying this amount of energy that is going to cause that would be required for one more of a solid substance uh, uh, to melt the solid substance when it is at its freezing point. Okay, so on the table here, we see that the stronger the intermolecular forces, the higher the melting point. Stronger the intermolecular forces, the higher the melting point is going to be for a given substance. The heating curve, we have seen it before a number of times. We were introduced to the heating curve, I'm sure, when we were doing our very basic science in grade 8. For those of us that were subjected to the grade system at the time. So in grade 8 to grade 9, I think that's when we looked at the heating curve. So here, to just explain quickly what is happening here, we've got, because I'll have to get back to this particular diagram at a later stage when I try to show you how to answer some questions. So between this point and the A point, the substance is in a solid state. So we're trying to see the relationship between temperature and time when we heat a solid substance. So that's a solid, it shows that the substance is still in a solid state. When it reaches point A, this is going to be the melting point of the substance. And then you see that at point A and point B, you've got a mixture of solid particles and liquid particles. So while the substance is changing its state from solid to liquid, the temperature stays constant because the gain in extra energy goes into breaking intermolecular forces and not kinetic energy. If you are able to remember where we're coming from, I showed you the Maxwell-Boltzmann distribution curves for the effect of temperature on particles of substances, where we had to establish that for the particles to gain the amount of energy, the minimum amount of energy that is needed, which is equal to the activation energy, the kinetic energy of the particles needed to be higher than the intermolecular forces of attraction that are holding the particles of the substance together. So this is what you see here, that the extra energy is being used to break the bonds, and the average kinetic energy of the particles does not change really from what it was at this point to any other value until all the intermolecular forces of attraction would have been broken. That's when the substance changes into a different state, which is a liquid, and then the same thing happens here also until all the particles change into all the intermolecular forces would have been broken, then the particles are going to change into a gaseous phase. So I'll get back to this at a later stage. The phase, the gas phase equilibrium introduces us to yet another formula, which we call the Hiss's law. So the Hiss's law requires that when we are determining the molar heat of sublimation of a given substance, which is the energy that is required to sublime one mole of a solid substance, we would need to know the molar heat of fusion of the substance and the molar heat of vaporization for us to be able to establish what that is. Okay. So while the diagram itself may not really have so much to say, to try and make us understand what this really is about, let me take you quickly to an example question that I designed that we are going to go through step by step. Okay.
So
So,
can you turn zoom the screen a bit?
okay, here.
Yes, yes. Okay, okay.
All right. So on this example question, when I look at all these things that we have looked at, quite a lot of things in terms of the principles and what the questions might look like as our example questions, and then I think about our colleagues who, some of whom might have just made it a habit to say, well, and probably they even boast to some of you when you are talking to them, they'll tell you, oh, online classes for me, they are not a thing for me. But I pity them. And even you who have consistently been attending these online questions, I'm sure you still, you also do pity them because it will be very difficult for them to even know how to maneuver through some of the questions. Because some questions may require that they should be, they would require that you answer them in a certain way that I would prefer myself, such that if you deviated from what is expected of you, you may not get all the marks. For them, they may be reading through textbooks. They just read at random. They get pages, that they find in books they read through, and they think that is the way to go. No, for you to survive, you need a better strategy. By a better strategy, I mean you should know when to be in the library studying, when to go to attend a lecture, when to go and sleep, when to go and eat. Okay. You have to have a proper plan on how to do everything. Then you're going to survive. Okay, I say this to you because I was a student also at some point, and I learned through some uh, of the ways of how to do things and survive through the hard way, where after you would have, well, struggled to understand some things, that's when you realize to say, oh, okay, so I need to manage my time properly. I need to be there when the lectures are being taught. Sometimes you would answer a question in a certain way, then you go to your lecturer, you ask, but I answered this question in this way. Then they'll just tell you point blank, well, this was not how the question was supposed to be answered. I would have preferred that you answered this question this way because this is what I taught you in your lecture and you are not there. How would you even begin to argue? How are you going to argue against what you will have been told to say? The question should have been answered the way you are shown in the lecture where you are not. So then you realize to say, oh, okay, so I need to be there when these lectures are being conducted. So luckily for them, they have you as their friends. They are very good friends who teach them everything that I have taught. Good for them. For those that are not here because it is not their fault, we sympathize with them. We really sympathize with them. So let's quickly go through this example question. So the question says, calculate the amount of energy in kilojoules needed to heat 3.346 grams of liquid water from 0 degrees Celsius to 182 degrees Celsius. Assuming that the specific heat capacity of water is 4.184 joules per gram per degree Celsius over the entire liquid range, and that the specific heat capacity of steam is 1.99 joules per gram per degree Celsius. So what do we need? We need to gather the information that we need, that is required to be used from the question itself, and see that we have everything there as we might be required. Then we will need this value. Okay, you see the 2260 and the 4.7 kilojoules per mole. So these two are constants which you might be expected to remember, especially when I bring a question like this one, or a question similar to this one in your quiz. For your quiz, I can assure you I'm not going to provide this constant in case I bring this question. I'm not saying this is a question that is going to come in your quiz. I am saying in case, worst case scenario. Okay. Worst case scenario, I decide to bring a question exactly like this one here. You would be expected to remember these two constants. Either one of the two will do the trick. It's going to work out for you. So, because the mass is given in grams here, you might need to stick to one of the two values. So in this case, we're going to stick to the 2260 joules per gram because the mass is given in grams there. Okay, so we'll talk about the other one later on, perhaps. So once we do that, we would need to apply the Hess's law. So the Hess's law would require 3 steps for us to be able to answer this question. So the first step would involve heating the liquid. Okay, so when you heat the liquid substance, the heating curve that I talked about, so this is supposed to be an arrow from 0 to 100 degrees Celsius. So when you heat your substance, it moves through those phases. So this is A, that is B there, this is C, D, E, and F. We saw this. Okay, so here, this is solid. There it is liquid. Okay. We are interested in the liquid, the gas portion of, but from here to there, it is solid, then it starts to melt. So between B and C, we said there's a mixture of solid and liquid. Then when we go to point C specifically, all the particles at point C are in a liquid state. All the particles at point D are still in a liquid state until they start to change into a gaseous state. Then at E, all of them are in a gaseous state. So between C and D here, this is where we have our temperature, as it were, from 0 degrees Celsius to 100 degrees Celsius before the particles change into a gas. So if you have noticed here, the state symbols are indicated as liquid here, okay, as liquid there and liquid there. So the water is changing its temperature from 0 degrees Celsius to 100 degrees Celsius when it is still in its liquid state. Okay, so what do we do there? Then we are going to apply, we're going to find the first change in enthalpy, the molar heat of vaporization in the first step will be given by the specific, let me just remove this. Okay, so you will need to use the mass of the substance, and the specific heat capacity of the liquid substance, water.
What's going on, guys?
Can be the
Network issues. I got kicked out. Let me just yeah, I know I got kicked out. Let me just project the work. And just open PowerPoint and project the work. It's a challenge that in the end, we are used to poor internet connectivity. Because even Zicta, that is supposed to monitor these internet providers, it's like they don't really care whether the services are poor or not. They just don't care. Okay. So we continue from where we ended. Yeah. So in the second step here, we will need to hit.
Sir, just repeat the first step where you are talking about the interview chat, something like that.
Okay. So yeah. So in the first step, let me just do this, then we'll go to the previous slide. So in the first step, we are saying, so in the first step, using this same diagram that we have here before we go to the previous slide, we see that the water is changing from, we are here, okay, and there, and here also. So the water from 0 degrees Celsius, which is the melting point, to the boiling point before the water changes into a gaseous state. It is still in its liquid state, but the temperature would have moved from 0 degrees Celsius to 100 degrees Celsius. And this is why the previous slide is showing us that we have the two states being the same, but the temperature is changing. So liquid here and liquid there, the temperature increases from 0 degrees Celsius to 100 degrees Celsius. So the difference in temperature between 0, okay, it keeps doing this. Sorry, you guys, it become responsive again. When I write something on it, it stops responding. This is going to waste a lot of time. Okay, sorry. Let me reproject again. Come on, stop doing this. Okay. Okay. Bear with me. Share the screen again. Okay. Yeah, so you have the first step. Our colleague says we go through the first step. So the first step, we have the change in temperature. Okay, maybe I shouldn't write anything. Let me try for the last time. If it misbehaves, then we will not write anything on the screen, which is going to be difficult for us now to follow clearly. Yeah, okay. So the substance is still in the same phase, but the temperature would have increased from 0 degrees Celsius to 100 degrees Celsius. So the difference between the two temperatures, 0 and 100 degrees Celsius, multiplied by the mass of the substance and the specific heat capacity of the liquid substance is what is giving us that value there. Okay. Are we together?
Sure, sir, sure.
Good. Then in the second step, you have your water. Okay. There, this is A, B, C, D, E, and F. So when you reach a temperature of 100 degrees Celsius, the temperature stays the same from D to E until all the particles would have had all their intermolecular forces broken, then they start to change into a different state. So the temperature stays the same at 100 degrees Celsius. This is why you see here we've got your substance changing its state from liquid to gas here. Okay. So the temperature stays the same. So what do? We are going to calculate or determine what is the change in enthalpy using the mass of the substance and the molar heat of vaporization for water, which was given as 2260 joules per gram. And the mass there, so the gram and the per gram would cancel, leaving us with an answer that is equal to 781,960 joules, which is conveniently expressed as 782.0 kilojoules of energy, which is quite straightforward. Then you will need to, the question says, you continued heating this substance to a temperature of 182 degrees Celsius. So when we go beyond the 100 degrees temperature, oh God, you guys, this keeps freezing. Why is it doing this? Maybe I've been using it for too long. I've been talking since 07 hours. Yeah, I've been using it from 07 hours up to now. It keeps collapsing. Just bear with me.
Can't you do a makeup tomorrow?
I make up tomorrow.
Yes.
The part that is remaining, yeah, the part that is remaining is small. Maybe I should just stop writing things on it. It's yeah. Let me try avoiding writing things on it. The part that is remaining is quite small. I was hoping that we should be able to conclude today itself. Okay, hopefully it will not collapse again. So yeah, you compute that. Then you notice that you will need to keep heating. You are heating from now 100 degrees Celsius to 182 degrees Celsius. So this is the steam that you are heating now because it has already changed. This is gas here. Take note. This is gaseous to gaseous. So you're still heating the steam from 100 degrees Celsius
Mark your
to
calendar for 25th July 2026 at NEPSA Sport.
You use the specific heat capacity for steam and the mass of the substance. The difference between 180 and 100 degrees Celsius as your temperature difference, then you will have 56.5 kilojoules of energy. Then you apply the
Mark your calendar
Hess's law. You need to add all the three steps.
for
The first step,
25th
the second step, and the third step will give you a total amount of energy that was needed as being equal to 983.3 kilojoules of energy. Okay, so for these types of questions, In case there's a question, anyone? Okay,
Yes, sir.
if there's no question then,
There's a question,
yes,
sir.
yes, please.
The unit there, isn't it supposed to be in joules? Or it's
The
okay
what?
living in that? The units.
The unit for the final answer. The final answer
Since,
here?
since
No.
the paper constant was in joules per graph.
No, it's the question itself. The question said,
Mark your
notice the way the question is phrased. It says in kilojoules.
Oh, all right.
So your answer should be in kilojoules. Yeah, so then one other thing that you need to pay attention to is the way the question would have been designed. So for your quiz, I might impose a restriction. I'll tell you, the constant that is to be used is this one here. Or let me just write something on this same slide here. So I tell you, the constant for change in enthalpy of vaporization is equal to 40.7 kilojoules per mole. This is the value that you are to use and not any other. So in that case then, this part here should be change in enthalpy for the second step should be equal to the number of moles multiplied by the change in enthalpy of vaporization, meaning that the mass of the water that you are given will have to be converted into moles. So you'll get 346 grams divided by 18.02 grams per mole. Then you multiply this with the 40.7 kilojoules per mole, so that the per mole here and the per mole there would cancel
12 to 16 hours.
Okay, so the per mole here and the per mole there would cancel out. The gram here and the gram there would cancel out. Then the final answer is going to be in kilojoules as the energy that you'll get. So you have to be on the lookout. If I impose a restriction, or just in case you are not able to remember the 2260 joules per gram value, you can still use this one if this is the one that you're able to remember. But you would need to change the grams that you have been given into number of moles for you to be able to execute the second step. Clear, isn't it? Okay, good. So for these types of questions, you will be given only molecules that you, compounds that you are familiar with. Okay, so instead of talking about water in the next question that you might see in your quiz or in your test, I will give you ethanol, for instance. Anyone who knows what the boiling point of ethanol is?
78.
Okay, good. The value is 78 degrees Celsius. So the next time you see a question like this one, we'll talk about ethanol. So what is the essence in knowing the boiling point? The essence in knowing the boiling point is that you would know where the demarcation is going to be. Because if you are heating ethanol, say from -2 degrees Celsius, how would you know what the difference is going to be that you would have to use in the first step? So the difference is going to be 78 minus -2. So this is what you would use in the first step. Then when the temperature stays constant as the phase is changing from, say, liquid to a gas, then you would have to find the change in enthalpy of your reaction when the temperature would have stayed constant, but there's a phase change. So from 78 to 78, what was the heat that was gained by the system when the temperature stayed constant, which is what we saw at this particular stage. So you would have to use the molar heat of vaporization for ethanol, okay, which you can get from the table. I'm sure there's on that particular table, there was a table where I had given these values. So you should be able to find that for ethanol or in any textbook. So for your assignment questions, you just have to dig up the value. For your quiz, you would have to master, probably you would just need to master two values, one for water and the other one for ethanol, both in joules per gram, or the one in kilojoules per mole for either of the two. Then for your test, if I decide to be lenient, I will give you the value or the values for either of the two. For your exam, definitely the value is going to be there because you will have a lot of questions and there will be a lot of things that would be required to remember. So we don't want to subject you to too much pressure by making you remember even the tiniest of things. So the constant might be given for such a question in your exam that is, of course, not in your test. So the remaining part, let me just cruise through what is remaining. And yeah, so we have what we call a phase diagram. The phase diagram for water, what is interesting on this particular diagram is the point that we call the critical point for water. So in other words, to try and define what this is, a phase diagram is a diagram that shows the states in which the different states in which a substance is going to exist. So either the solid state, the liquid state, or the gaseous state. And these regions are stable regions. And the lines that you see there are the demarcations, which show some coexistence of some sort. At 1 atmosphere, water boils it's got a normal boiling point of 100 degrees Celsius and a melting point of 0 degrees Celsius. So it's going to
16
exhibit
hours.
some weird behavior where all the phases are going to exist at some point. And this particular point is where you have a temperature of 0.01 degrees Celsius and the pressure of 0.006 atmospheres. Okay, so are you expected to know these values? No, not really. All that you would need to remember is the term critical point. So we will tell you that water has got a temperature and a pressure at which all the three states exist. Okay, all the three states exist. What name is given to this point at which all the three states are going to exist? That is the solid state, the liquid state, and the gaseous state. It's called the the triple point. So the triple point is the point at which water exists in all the three states, and the temperature is equal to 0.01 degrees Celsius, and the pressure is equal to 0.006 atmospheres. When you compare this with another substance, which is carbon dioxide also has got a critical point, a triple point rather. So this triple point, the temperature is negative 55, 57 degrees Celsius. The pressure is at 5.2 atmospheres. Okay. What is interesting about carbon dioxide is that when you look at its application in real life, you see that take for instance what is the fire extinguisher. So fire extinguishers store carbon dioxide as a liquid under pressure, because at 1 atmosphere, carbon dioxide is going to sublime directly into a gas, but under pressure, it remains as a liquid. Okay, allowing dense storage and then rapid expansion to called, gas carbon dioxide that manages to put out fires when it is allowed to come out of the cylinder. Okay, so in the remaining 2 minutes, let me just conclude with this particular slide that we have here. Water, yet again, exhibits some very interesting behavior that is weird. When you look at this particular curve, we have the liquid vapor curve, which is on the right this side here, which slopes upwards. So if we increase the pressure above 1 atmosphere, the intersection moves up to the right here, slightly up there. So this indicates that the higher the pressure, the higher the boiling point. for water. Okay, and this explains what is the principle behind a pressure cooker. For our girls who enjoy cooking, they know what a pressure cooker is. The boys may not really know it because they are told most of the times, do not go to the kitchen. You are going to burn the food, or you will put too much salt in the food. So the girls might know better what. Pardon? Someone say something? Okay, yeah. So the girls know a pressure cooker better. So in a pressure cooker, when you put your food in the pressure cooker and you close it tightly, the temperature increases. As the temperature increases, the pressure also increases. So at a very high pressure, the food that you might expect to cook, say, in 2 hours, may just cook under 45 minutes, and it is ready. Okay. Especially for beans, your beans might have to be put on heat for almost the entire day for it to be ready. But in a pressure cooker, it might manage to cook just in 120 minutes. Okay, which is quite a short period of time. That is just slightly 2 hours and plus minutes there. The beans is ready. Okay, this is because when the pressure is higher, the temperature at which the water is going to boil increases. It goes beyond 100 degrees Celsius, which causes the bonds that are holding the molecules in your food to break far much faster. Okay, when you look at the melting point, on the other hand, the higher the pressure, the lower the melting point of a substance. So this explains the reason that you are able to see those who move on ice, the ice skaters, they're called skaters. They're able to slide and they keep moving. This is because those shoes that they wear, that they move with on ice, have got sharp, the pointed ends on the bottom part. So those pointed ends are going to exert some high pressure onto the ice, which reduces the melting point of the ice, and they're able to slide as they do, like that. Okay, so with that, my good friends, I would like to surely announce that we have come to the end of the first part of our component, and I'll put the notes together nicely and share them with you. Next week, we will start last topic on our component. So even if, of course, the next week is supposed to be our week, if I'm not mistaken. So in 1 week, if we can finish what is remaining, then we would have done everything within the time that we were given. If any part is going to remain, then we might have to come up with some, extra time outside of the normal schedule to do what is going to remain. So I will see you next week. You have a question? Is there a question from someone? Or it's just
Yes,
the mic that
it's
is
not
on?
a question, sir. It's a
Okay,
request.
please.
Yes, some of us, okay, me personally, we're asking for the notes before we start the other topic so that we connect properly because we need to revise.
Okay, the notes will be arranged nicely and be availed to you. But if I take too long, please do not, strangle me by my neck to say, you said you're going to send the notes the following day. It's because, I have you guys, I have another group, then I have two other groups in 1010. I have got the second years, I've got the third years and the fourth years. So everyone is crying for notes. Which notes you guys are supposed to, if anything, manage to organize on your own using the recommended textbooks. But I will still send the notes to you. I assure you. Okay. When I get a chance.
So,
Yes, please. Yes,
so,
please.
so what's the next topic?
It's solution properties.
Okay.
All right.
All right.
All right. So blessings. I'll send the notes. Don't worry. Okay. All right. Good day, you guys. I'll see you next week.
Thank you.